So last lecture I talked a little bit about epidemiology and the role of epidemiologists. I also mentioned how epidemiology has really grown as a field of medicine. In this lecture I'll talk about the mathematical and physical models that are used to predict the spread of disease over the globe. So there are certain key questions that need to be answered in order to make effective predictions of the spread of disease. Where does the pathogen originate? What country? What area of the world? Where will it travel? Will it be halfway across the world tomorrow? When will it arrive somewhere else? How many people will be affected in the population? The first model I will explain is the most simple one, the reaction diffusion models. It was used to map out the spread of disease in the Black Plague in Europe. Some of the pros, very simple. It shows a good understanding of the spreading process of disease and assesses key properties such as spreading speed or difference in location. It's also kind of specific about each disease. Some of the cons, it's too abstract for modern day complex networks. It doesn't take into account that we use air travel, that people can easily get to another country. Spatiotemporal dynamics, it doesn't really put into the fact that there's different space and time changes that can affect how a disease will spread across the globe. And it's very difficult to measure because air travel is just so easy nowadays. You can't really put a block on it. Next are computational models, which include simulations used with computers. It's a lot more complex. It uses a lot of demographics, including human behavior patterns, disease-specific processes, lots and lots of different mobility patterns, human, and epidemiological data. Because it's more disease-specific, it's a lot better of a method to use than the reaction diffusion. The cons, there's a lack of understanding of the driving forces, space and time. Anything can change at any time. There are too many factors included. So how a disease spreads, there's too many different ways that it can change. So it's just too complex to be able to understand. It's also useless when there's little known about the disease or the epidemic. The combination model is what this paper is suggesting we use. It measures effective distance. What is an effective distance? It's very different from geographical distance because it's not exactly how far away a location is, but it takes into account the arrival time, and it's also using global mobility network. The key benefits of being able to use this type of model is it'll more accurately and efficiently show the origin of the disease, and it helps develop relief efforts a lot more sooner. These maps are both of simulation of the disease originating in Hong Kong. In A, each of these colored nodes just helps differentiate between the different countries of the world, different geographical locations. Each of these gray lines represents over 4,000 different airports and over 25,000 different connections to these different countries. Figure B just shows the distribution of the disease for the origination of Hong Kong. So it's basically the same as this, but it's not as easy to understand because it's not showing how it's getting from one location to the other. These three figures are not using effective distance, they're using geographical distance. So DG stands for geographical distance, and TA is arrival time. This red bar going through the nodes just is where the data was being used on the previous map. It's the simulation. These two are using real data, testing it against the model for H1N1 in 2009 and SARS in 2003. Each of these nodes is, again, the color doesn't matter, it's just differentiating between the different locations. Its variability is really high right here, which shows that this model, using the geographical distance and arrival time, is not as correlated. So it doesn't exactly show you where the origin could be. It gives you kind of an approximate, maybe these couple locations, but it's not going to be very effective in helping you find the origin. So in this H1N1 model, it was placed in Mexico, but because of all these other locations all over the place, it shows that these locations, even though they're in the same geographical distance away from Mexico, they all receive the disease at different times, which just doesn't make sense with the model hypothesis. And the same thing with SARS. China was the first, and then all of these locations, all the nodes are in different areas, have different arrival times, even though they're around the same geographical distance away from China. These models are of effective distance. With this model, you're able to see the spreading speed and the location of how fast these diseases are able to spread across the globe. Again, they're using Hong Kong as the origin, which is that center node right there. And these lines all represent effective distance and the shortest path to each different node, which are the different geographical locations around the world. Figure B is just a quick representation of the simulation showing how fast these diseases will spread across the globe within a certain amount of time. As the time goes up, more and more susceptible persons are likely to get infected. And this ring is just so, it shows a linear relationship. Compared to the other geographical distance versus arrival time, it's just all over the place. This one's just more lined up and it shows a better accuracy of the origin. Now this method isn't exactly spot on because there are still other factors and space and time dynamics that may interfere with how disease spreads, suddenly changes course, but it's a lot more effective than using geographical distance. You can see this hash line right there, it's the relationship, the linear relationship of all the data. The closer you are to this, to the 0 mark, it helps show exactly where the origin is. Over here, the real data of H1N1, Mexico, with the US closely following. And then for SARS, China, the origin. For these, the arrival time is approximately 81 days. Both of these have the exact same nodes in the same spots, but this one's just labeled all the international airports that could possibly be the origin of the disease. The different codes are different airports. ORD stands for Chicago, YYZ is Toronto, ATL Atlanta, MEX Mexico, SYD Sydney. Each of these have an equal chance of being the origin, but using the effective distance model, you're able to pinpoint which one was the original location. In this one, it was Chicago, but in A, Chicago's not put on the map because it was just hypothetically showing you a visual representation of where it could possibly originate. It's kind of hard to tell. I know this looks complex, but they're all pretty related, and I'll just tell you the important part. The red is all that matters. With effective distance, you're looking for the one that lines up the best, the most linear relationship. Chicago was found to be the origin. As you can see with all the others, there's a lot of variability. This method of charting, there's quantitative charting with just the nodes on the graph, but with this one, you're able to see the data qualitatively, so it's a lot easier if you're a visual person. Two quantitative charts using real data, H1N1 and the SARS outbreak. So this one's a little bit different. The two variables, we have the arrival time and effective distance on one, and rank of the country on the other. The lower the rank, the more likely the country was to be the original location. For the H1N1, like I said, it was Mexico, with the USA following closely behind. but it's the lowest rank. These models are just another way of showing the last couple slides, just represented differently. It does have different variables on this one. They're all measuring effective distance. But the red X is the original location, what was found. This is the simulation, H1N1. And this is a different one. This is E. coli, foodborne illness found in northern Germany. The variables on this one, we have sigma F, which represents the variance of effective disease, or effective distance. And we have micro F, which is the mean of effective distance. If you have both low mean and low variance, then that was the location that was found in the origin. For H1N1, there was 4 different weeks that were documented. And as time went by, it was a lot harder to tell the origin. So many things are changing, it's a lot harder to differentiate between the origins. So that's why Mexico just slowly becomes less clear as the origin. Other countries are starting to dominate, but you just can't tell the difference. With the E. coli, the data was very varied because it's a different type of mobility network. This is foodborne. Food travels differently than humans do. It was a lot harder to test the model on that certain case. Thanks to modern air travel, disease and pandemics have never been easier for spreading across the globe. With the reaction diffusion models and computational models put together, efficiency is really easy to come across for predicting the origin of disease. It can also help with the other key questions, cause, how fast it's going to travel to another location. Effective distance is greater than geographical distance. I showed that in the tested models. It's a lot more accurate with being able to pinpoint specific locations. It's more disease specific. And these models were tested and confirmed as practical. So epidemiologists can use this model as suggested by the research scientists. I would like to acknowledge Dr. Dirk Brockman and his co-author Dirk Helbing for their research. And this is a cover of the magazine that I got the article.